In section 5 of chapter 1, we're going to be going over checking solutions of systems of equations. So, in the past I asked you what solutions mean. We're going to be applying that right now. What does it mean to be a solution to a linear function? Well, it's important to recognize what graphs are. A lot of students, especially on the honors track, they just get so lost in the rigmarole into the process that they forget what they're doing and why they're doing it. So I have this equation y equals 4x minus 9. A lot of you could tell me so y-intercept is negative 9, slope is 4, so you go up 1, 2, 3, 4, right 1. You could also go up another 1, 2, 3, 4, right 1, 3, 4, right 1, 1, 2, 3, 4, right 1, and so on and so forth. And you can create this line. But sometimes students get lost in what the heck is the point of this. The purpose of graphs is they are a visual representation of all of the answers. Because that equation has a bunch of x and y values that if you throw it into the equation will produce true mathematical statements. That graph is a visual representation of all of the answers that work. If you plug in 0, negative 9 into this equation, you would get a true mathematical statement. If you want to determine if a given coordinate is a true mathematical value for that equation, you take that coordinate and substitute it into the equation. When you do that, you would get negative 1 is equal to 4 times 2 minus 9. And if we simplify that, we get negative 1 equals 8 minus 9. Negative 1 equals negative 1. It's a true mathematical statement. Negative 1 does equal negative 1, which is why that coordinate is right here. It's on the line if you graph it. There's this connection between the algebra and the geometry, between the algebra and the graphing. The graph tells you all of those coordinates. What we're going to be doing today is testing coordinates. We've done that in previous skills. Now we're going to take it a little bit further. So what does it mean to be a solution to a system? Whenever you hear me or any mathematician say the word system, that's just my way of saying more than one. So a system of equations is just my fancy math way of saying instead of dealing with one equation, we've got two. That's all system means. So a system of equations means you got two equations. Maybe three, maybe four, but at least two. So I've already graphed the green line. Now I'm going to graph the purple line. The purple line has a y-intercept of negative 3, has a slope of 5 over 2, and it would look something like this. Again, this dot would be a solution to this equation. This dot would be a solution to this equation. A solution to a system would be a dot that they both have in common. That is going to be where the two intersect each other. So in this case, it's at 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. It is at 4, 7. And if I wanted to verify that that was a solution algebraically, all I got to do is take that coordinate and plug it into each of the equations and verify that it's a solution for both. So this would turn into 7 is equal to 4 times 4 minus 9, which is 7 is equal to 16 minus 9, 7 equals 7. It checks off. So that coordinate is a solution to the green equation. Then I also have to check it for the purple equation. Substitute it in, and we would get 7 is equal to 5 over 2 times 4 minus 3. That means 7 is going to equal 20 over 2, because it's top times top, bottom times bottom when you're multiplying fractions, minus 3, 7 is going to equal 10 minus 3. 7 equals 7. It works for both. So yes, this is a solution to the system. It's a coordinate that validates both functions. Here's what we're going to be doing today in this lesson. It's going to be rather short and sweet. I am going to give you the system. I'm going to give you both equations. I am also going to get you the coordinate. You are going to determine, is that coordinate a solution to the system? The way we do that is just like I just got done doing. I'm going to take that coordinate and plug it into the first equation. 2 is equal to 3 times 1 minus 1. I want to see if this is mathematically true. 2 is equal to 3 minus 1. 2 is equal to 2. It checks off for the first equation. Then I've got to do the same exact thing for the second equation. 2 is equal to negative 5 times 1 plus 7. 2 is equal to negative 5 plus 7. 2 is equal to 2, so it works here as well. If you stop at this point in the problem, you will not get full credit, because the questions will be asking, is the given coordinate a solution to the system? I haven't answered that yet. I said it's a solution to the first equation. I said it's a solution to the second equation. I've yet to say anything about the system. So you have to finish it with, yes, that is the answer. It is a solution to both equations. So for the second problem, I'm going to do the exact same thing. In order for that coordinate to be a solution to the system, it must be a solution to both the top equation and the bottom. So when I plug it into the top equation, I am going to get 5 is equal to negative 4 over 3 times negative 3 plus 2. That means 5 is equal to positive 12 over 3 plus 2. 12 divided by 3 is 4. 4 plus 2 is 6. It does not work for the first equation. So then it really doesn't matter if I plug it into the second equation. If it works or it doesn't work for the second equation, it doesn't matter. This is not going to be a solution to the system. As soon as it fails one of the equations, you stop. The answer is no. You are done. Because we're asking, is this a solution to both equations? Not one or the other. It has to be both. So if it doesn't work for one and it's your first one you're attempting, you don't have to try the second one.